All right, so today we are going to look at related rates. So this is an application of implicit differentiation, but it's a way to look at like things that are happening, and we kind of take a snapshot. At a particular instance, we can observe some quantities and we can derive some formulas that help us model what's going on. And we can actually do more work with that. So our setup here, suppose that x is a differentiable function of t and that y is 6x squared plus 3. So when we did implicit differentiation, we took the derivative like normal, but anytime we took the derivative of y, we put dy dx next to it as part of the chain rule. Now, whenever we take the derivative, we're taking the derivative with respect to t. So we're going to put either dy dt or dx dt everywhere when we take the derivative of that particular variable. So when we look at our function y equals 6x squared plus 3, and I'm going to take the derivative of this. The derivative of y is dy dt. The derivative of 6x squared will be 6 times x squared is 2x times the derivative of x is dx dt plus 3. The derivative of 3 is, it's a constant, so its derivative is 0. So our formula for dy dt is 12x times dx dt. Now, as part of the follow-up, it says if dx dt is 8 when x equals 2, then they want us to figure out what dy dt is at x equals 2. So dx dt might be changing depending on what position of x we're at, but they're telling us for our snapshot, when we freeze on x equals 2, our dx dt is 8. So these are substitutions we can make into our formula. So x is 2 and dx dt is 8. So we get 8 times 24. 192. So if they give us the function, we can take the derivative. We just have to remember our chain rule everywhere, putting the derivative, the dt, it's typically with respect to time. Like we call this related rates because these are quantities that change per some unit in time. Go for it. So when we did the derivative of 6x squared, we had the constant 6 times the derivative of x squared is 2x. But what we're taking the derivative of, like with respect to, is t. So normally this would be like times dx dx, which would just cancel and be 1. But we're taking the derivative with respect to a different variable, time. So like I think of the 6x squared as 6 times things squared. So then the derivative of that is 6 times 2 times thing times derivative of thing is dx dt. So it's just an added extension of our chain rule. Help or no? It's okay to say no.
Like it says, suppose that X is a different, like is X the function?
So they're saying it like, suppose X has some formula in terms of T. We don't know what that formula is, but we're just kind of assuming that it is something in terms of T. Okay. All right, so now we've got basically the Pythagorean theorem. Suppose that X and Y are differentiable functions of T, and we have our formula. And then they give us a whole bunch of givens over here. So we're going to focus on the formula and taking the derivative of this formula. So let me write it down. All right, so when I take my derivative, the derivative of z squared, I bring my power down and subtract 1, so that'll be 2z's, times z, the derivative of z with respect to t is dz dt. The derivative of x squared is 2x times dx dt, plus the derivative of y squared will be 2y times dy dt. So our derivative formula is very ridiculous, but that is what the math tells us to do. So when I look at the information they told me, they gave me dx dt and dy dt, and they gave me x and y. So everything on the right side of the equation, I have something to substitute. But on the left side of the equation, I have 2z times dz dt. So this 2z, I need to know what z is in order to figure out and solve for what dz dt is. So I know x and y though. In my snapshot, x is 5 and y is 6. And I know a formula that tells me how to relate x and y to z. So I'm going to take those numbers and solve for z using the original formula. So we have 25 plus 36. So z squared is 61. And then we square root. And we normally have the plus or minus conundrum here. When in doubt, I generally just go with the positive. But to actually pick, we need to know more information about the problem. All right, now we're going to fill in all of our numbers, and then we'll solve for dz dt. So 2 times z is the square root of 61. X is 5. Dx dt is 4. Y is 6. And dy dt is 7. So we get 40 and 84. So 124. And then we just divide by the stuff being multiplied to dz dt. So we have 2 square root 61 that we're dividing by. And I would leave the answer like that. Weber will take unrationalized fractions. Now we could multiply by the square root of 61 over the square root of 61, and that's fine. We can actually, the 124 divided by 2 does reduce. So we could do that, but Webwork should take the fraction even unreduced. But that would be 62 over the square root of 61 if we reduced it. So questions on how this one shook out? All right. So our next one, a little bit different. We've got a curve and a particle is moving along this curve. And its x coordinate is changing at a rate of 5 centimeters per second. At what rate is the particle's y coordinate changing when the particle is at the point where x equals 4? So we've got a whole bunch of words. So we've got to practice translating the words we're seeing here into the information that we need to solve the problem. So when they tell us the x coordinate is changing at a rate, then the rate is our dx dt. So dx dt is 5 centimeters per second. Then they're asking at what rate is the particle's y coordinate changing? So that is dy dt. That's our unknown that they want us to figure out. And then it says, when the particle is at the point where x equals 4, so x equals 4 is our freeze frame snapshot when we're looking at this. So let's start with our function. Y equals 4x squared plus 7. So we're going to take the derivative of this with respect to time. So the derivative of y will be dy dt. Then the derivative of 4x squared will give us 4 times 2x times dx dt. Plus 7 is a constant, so the derivative of a constant is 0. All right, so I had 4 times 2x times dx dt. So 4 times 2 times x in our snapshot was 4, and dx dt was the 5 centimeters per second. So we have 32 times 5, 160. So the x is moving at a constant rate, but how quickly the y coordinate changes depends on where we are on this curve, how quickly, how steep the graph is at any particular time. So questions on how we translated from the words into the given notation, the derivative, substituting, anything at all. All right. Now this is where related rates get their bad reputation. So up until now, they gave us the function that we were going to take the derivative of. Now they're just giving us a description of a situation, and we're going to have to find the equation. So we have an 8-foot ladder is leaning against a wall. So let's doodle a picture. Got my ground. There's my wall. There's my ladder. And I know that ladder is 8 feet long. So it says if the top of the ladder slides down the wall at a rate of 2 feet per second, how fast is the bottom of the ladder moving along the ground when the bottom of the ladder is 5 feet from the wall? So we're talking about the top of the ladder is sliding down the wall. The bottom of the ladder is moving along the ground. So if the top starts falling down, that's going to push the bottom out. So we've got some directions here. We've got this is going down, and this is going out. So when we're marking our motion, that's our rates. So the top is sliding down at a rate of 2 feet per second. And then we want to know this rate for how fast the bottom of the ladder is sliding out. And then our snapshot is, they say when the bottom of the ladder is 5 feet from the wall. So we have that 5-foot mark from the wall to the bottom of the ladder. And I know the ladder itself is 8 feet long. And then I've got how high up the wall the ladder is positioned. So I'm looking at all of these distances. The distance from the bottom of the ladder to the wall, the distance from the ground to the top of the ladder, and the length of the ladder. So I need to label those lengths. So we can pick whatever letters we want. In this case, it's a right triangle, so I usually just go with A, B, and C. So now that I've labeled these, my ladder sliding down the wall at 2 feet per second, that is dB dt. dA dt is what I'm looking for. That's my unknown. So when I look at this ladder sliding down the wall, my B distance is going to be changing. My A distance is going to be changing. Is my C distance changing? No, because that's the ladder. The length of the ladder does not change here. So since C is constant at 8 feet, that means dC dt is not changing. It's always 8 foot, so there is no rate of change to that. All right, so now I need an equation that relates A, B, and C. So what do we know about the lengths of the sides of a right triangle? I mean, I picked A, B, and C on purpose. Yep, Pythagorean theorem. So when we take the derivative of this formula, the derivative of A squared is 2A times dA dt plus the derivative of B squared is 2B times dB dt equals the derivative of C squared is 2C times dC dt. So we took our derivative, each one got its own chain rule related rate next to it. So now I want to check the things I know and see if there's any missing variables. So over here, I knew that the ladder was 5 feet from the wall. So that is A. And I know C is 8. But when I look at my formula, I also need to know what B is. So we're going to have to use our formula, the Pythagorean theorem, to solve for B. So B squared is 39. So B is the square root of 39. So I know all of my snapshot values. I know that dB/dt is 2 feet per second. And I know that dC/dt is 0 because the latter is a constant length. So now I'm just going to fill in all of those things that I know. All right, so I have 10 dA/dt plus 4 square roots of 39 equals 0. So I'm going to minus and then divide. So the 4 and the 10 reduces to 2 and 5. Now I got a negative number here. Now we can get positive or negative rates just depending on how we look at our snapshot, our freeze frame. So when I go back and look at the original setup, when the ladder is sliding down the wall, so that 2 feet per second, when I look at B, is B getting bigger or getting smaller as the ladder slides down? Smaller, because it's going down. So like eventually B is going to equal 0. So when I plugged in that 2 feet per second, I probably should have been plugging in negative 2 feet per second. So there is a direction that sometimes comes into play here. So if I typed in negative 2 square root of 39 over 5 and Webwork was like, no, I hate your answer, then my next gut would be like, oh, maybe I did the sign wrong. So the fact that we got a negative here means whichever direction B is going, A is kind of going the opposite direction. Opposite being a relative term here, though. B is getting smaller, so the rate should be negative to indicate that it's getting smaller. A is getting bigger, so our rate of change on A should actually be positive. So if I change my dB/dt to negative 2, then this would be negative 4 square roots of 39. And then that would change this to adding 4 square roots of 39. And that would make the result positive. Now, most of the time we're looking at something like getting bigger everywhere or getting smaller everywhere. So paying attention to the sign on the rate usually doesn't have that big a deal, but it is something we should be paying attention to. So questions on how this shook out? All right. So let's take a look at our next one. You and a friend are riding your bikes to a restaurant that you think is east. Your friend thinks the restaurant is north. You both leave from the same point, with you riding 17 miles per hour east and your friend riding 12 miles per hour north. After you have traveled 3 miles, at what rate is the distance between you and your friend changing? So weird setup here. So you and your friend start from the same point. You go east, your friend goes north. So you're riding 17 miles per hour east. So we know that the east direction is changing at that rate, 17 miles per hour. Our north direction is changing at a rate of 12 miles per hour. Then it says, after you have traveled 3 miles, so we're fixing this distance at 3 miles. At what rate is the distance between you and your friend changing? So they're talking about the distance between you and your friend. So we need that in our figure. I'm going to call it a capital D for the distance between them. And they're asking us the rate that this is changing at. All right, so I need labels for our diagram here. So I called D for the distance between you and your friend. I need something for the other two. It truly doesn't matter what. You just, you know. So we could do X and Y since I've got a horizontal and a vertical distance. All right, so how do X, Y, and D relate here? So X is our horizontal distance, Y is the vertical distance, and D is the diagonal distance. Now, since I'm going north versus east, I know it's a right angle between those two directions. So this is a right triangle. So what do I know about the lengths of the sides of a right triangle? How do they relate together? So Pythagorean theorem again. So now I've got x squared plus y squared equals d squared. Now, I'm going to take the derivative and I'm going to have 2x dx dt and 2y dy dt, 2d dd dt. Well, we may as well just write it. So when I look at my derivative, I know x. X is my 3 miles. I know the rate at which x is changing. X is increasing at a rate of 17 miles per hour. And I know y is increasing at a rate of 12 miles per hour. But in my formula here, I need to know what y and d are. And right now, I don't know those. So we're going to have to use a little practical knowledge. So when you've traveled 3 miles, your friend has also traveled some distance. It's not the same distance because you and your friend aren't biking at the same speeds. But when you've gone 3 miles, a certain amount of time has passed. That's the same time that your friend was biking north. So we're going to use our knowledge about how speed works to figure out that time. And then we're going to use that time to figure out the other side. And then we'll use our Pythagorean theorem to figure out the distance on the snapshot when you're 3 miles away. So I'm looking for how do distance, time, and speed relate. And for me, the way I remember it is that speed is typically written like miles per hour. Miles is a distance. Over a time. So my speed is 17 miles per hour. My distance is the 3 miles. And then my time is what I want to solve for. So we got to multiply both sides by t, and I end up with t times 17 on the left. So then I also divide by 17. So I have t equals 3 over 17. And the miles will cancel out. And we're left with per hour, which becomes hours. So our time is 3/17 of an hour. So that means our y distance is going to be the 12 miles per hour times the 3/17 of an hour. So y is 36 over 17. And now that I know x and y, I got to figure out what my distance is in my snapshot as well. So I've got 3 squared plus 36/17 squared equals d squared. Yay, calculator that does fractions. So 3 squared plus, open parentheses, 36/17, close parentheses squared. Whoa. 3897/289. And then we square root. And all I'm getting is a decimal, so decimal is fine. 3.67211, blah, blah, blah. So I finally have my 3 snapshot distances. I've got my rate of change for X and Y. So we're going to fill those pieces in. And this is where we're gonna make a lot of use of our calculator. So 2 times 3 times 17 plus 2 times 36/17 times 12 equals some ugly number. 152.8235. And then I have 2 times that 3.672. That is 7.344. I end up with 20.80865. And this would be miles per hour. And all 3 of those rates are increasing. They're all getting bigger, so they should all be positive. So the sign here makes sense. So what questions do y'all have on how that craziness shook out? Yeah, let's see what the next one does. So we've got a bottle rocket. You stand 25 feet from a bottle rocket on the ground and watch it as it takes off vertically into the air at a rate of 19 feet per second. Find the rate at which the angle of elevation from the point on the ground at your feet and the rocket changes when the rocket is 40 feet in the air. All right, so let's start with our picture. So we've got our rocket shooting up, and we know that it's going up at a rate of 19 feet per second. And then we know we're standing 25 feet from where the bottle rocket took off. And then from the point on the ground at your feet to wherever the rocket is at, so when it says the rate at which the angle of elevation changes. So the angle of elevation here, well, I got to give it a name, so I'm going to call it theta. So they're asking us to figure out d theta dt. That's what they want to know. And then they're telling us, look at when the rocket is 40 feet in the air. All right, so this is 40 feet. So I've got, again, we assume the rocket goes straight up, even though fireworks are not that reliable. But I've got a right triangle, two sides, and an angle. So I need to call these sides something. So I've got some labels. So I'm just going to be boring and go with X and Y. So I need an equation that relates X, Y, and theta. So what do I know about those three things, X, Y, and theta? So law of sines helps us relate side lengths to the sine of the angle. So law of sines would give me like the two side lengths and the angle, but law of sines would also introduce another angle. And I don't want to figure out like the rate at which that angle is changing because it is also changing at some particular rate. But it is a right triangle, right? So when we have right triangles, we don't like law of sines works for any triangle. But when we're dealing with right triangles, we can actually just straight up use our trig functions. So when I'm looking at a right triangle and I have my theta labeled down here on the bottom right, what would I call y in relation to theta? So y is adjacent to theta, y is opposite. And then what is x? Yep. So what do I know about the opposite and adjacent side in a right triangle? Opposite and adjacent? So if you don't remember, there's SOHCAHTOA, but then you have to remember how to spell SOHCAHTOA, which can be problematic, especially if you're dyslexic. So I have a mnemonic for it. It's some old hippie caught another hippie tripping on acid. So sine, old hippie, O over H, cosine, caught another hippie, A over H, tripping on acid, tangent is O over A. So O and A, this is our tangent. So that is the function that relates these three quantities. The tangent of theta is our opposite side over our adjacent side. Well, we called our opposite side y and our adjacent side x. All right, so I know the rate at which y is changing. Now our x down here, does x change? Nope, we're always 25 feet on the ground from the rocket. No, sorry, not 25. So I know my two rates of change. I want to find d theta dt, but I know my x and my y in my snapshot. I don't know my theta in my snapshot. So I do need to calculate theta. So we're going to use our function that we determined, tangent of theta equals our y is 40 feet and our x is 25. So now, what do I do to this function, tangent of theta equals 40 over 25, to get theta by itself? So how do we calculate to figure out what theta is going to be? So tangent is a function, inverse tangent is also a function. So we don't say multiply by it. We say apply it or take the inverse tangent of both sides. But yes, that is the thing we want to do. And I know that feels like a pedantic correction, but if tangent is something I could multiply by, then tangent is something I could divide by. But if I wrote divide by tangent and tried to type it on the calculator would be like tangent of what? And then we'd be like, oh, that's not what I wrote. But if we do tangent inverse of the thing, this I can type on the calculator. But notice like where I squeezed in the inverse tangent, it's on, like it's before the 40 over 25. So this is going to be some number. Now, what they didn't tell us is if we should be in degrees or radians. So if this was a problem from WebWork, WebWork would tell us if they wanted it in degrees or radians. Generally, though, if you're not sure, unfortunately, the answer is go with radians. So we're going to have to switch over to radian mode. And then our inverse tangent of 40 divided by 25. So we've got 1.012 radians. All right, so now I've got all my snapshot pieces. I can take my derivative. Now, I'm going to use a kind of sneaky trick here because I'm lazy. So before we take the derivative, since x is constant, it never changes, I can actually fill that in before I take the derivative. So I can treat it as a constant. So that means this y over 25 is really 1/25 of y. 1 over 25 is a constant being multiplied to the y. So now, if you look at the original equation, if I take the derivative of that as is, I'm going to have a quotient rule, which is not wrong. It's just a whole lot of extra work that we don't actually have to do because dx dt is going to be 0 and it's going to cancel out a bunch of stuff. So I'm going to take the derivative of this equation. So the derivative of tangent is secant squared theta times the derivative of theta is d theta dt equals, so the 1 over 25 is our constant, times the derivative of y is 1 times dy dt. All right, now we're going to fill in stuff we know. So we have secant squared of the 1.012 radians times our unknown d theta dt equals 1 over 25 times y was changing at a rate of 19 feet per second, so times 19. So to get d theta dt by itself, I'm going to divide by secant squared. Now, secant isn't a button on the calculator. So we're actually going to have to manipulate this a little bit to actually get something to write for d theta dt. So secant is 1 over cosine. So I can write this as, so the 1/25 times 19 is 19/25. Divided by, instead of secant squared, I know secant squared is 1 over cosine squared. But if I type cosine squared like that on the calculator also loses its mind. So we also have to pull the squared outside. So we end up with a lot of parentheses. All right, so we start with our 19 divided by 25 divided by open 1 divided by open parenthesis cosine. Then I'm going to go back and hit my 1.012 ugly answer. And then I had to close my parenthesis twice and then square that and then close it one more time. So sometimes we get weird questions that are dealing with the rate at which an angle is changing. But we used our right triangle, knowledge of right triangles, trig functions. We came up with an equation that related the quantities and went working from there. Now, figuring out that function can feel like really awkward because there's so many different formulas you guys have been exposed to. So trying to land on what's the one right formula that only relates these quantities can feel a little awkward. You'll notice though, like most of the examples we've dealt with though, it's been right triangles. And that's because whenever we're looking at a naturally occurring thing, there's typically natural right angles that occur. And when you start connecting the dots, you very often get a right triangle. So Pythagorean theorem, if you're only looking at the distances, or one of our trig functions, if we start looking at the angle changing. All right, so we got two more. So this means I'm going to have to record an extra video really late tonight. But the volume one is a very classic related rates question. So we have a tank in the shape of an inverted right circular cone that's leaking water. The dimensions of the tank are a height of 14 feet with a radius of 4 feet. All right, so our inverted cone looks like an ice cream cone. So I know overall the tank is 14 feet tall and my radius at the top is 4 feet. So how fast does the depth of the water change when the water is 12 feet high if the cone leaks at a rate of 8 cubic feet per minute? All right. So we've got depth of the water when the water is 12 feet high. Okay, so let's put our water height in there. So our freeze frame is when the water height is at 12 feet. It wants to know how fast is the depth of the water changing. I mean, so they say depth, but that's still height to me. So I'm going to call this H. And then our unknown here, they're wanting us to figure out dH dt. And then the other rate they gave us was 8 cubic feet per minute. So when we have cubic feet is measuring what kind of thing? What idea? Hmm? Yep, volume. So like just feet is a distance, feet squared is an area, feet cubed is volume. So this 8 cubic feet per minute, this is the change in volume with respect to time. So dV dt, which gives us a clue for what formula we're going to want to use. We're going to want to use the volume, which means we got to remember the volume of a cone. So the volume of a cylinder is area of the base times the height. Our base here is a circle though. So pi r squared times the height, and then a cone gets a 1/3. So we've got a formula for pi r 1/3 pi r squared h for the volume. So I've got my h in there, and dH dt is what I wanted to solve for. But I also have a radius in there. So let's see. So if I took the derivative of the volume formula right now, I'd end up with dr dt and dH dt. And I could do that, but then I'd need some other formula to figure out what dr dt is. But if I can figure out some other formula that relates R and H, I can make a substitution before I do the derivative, and then I won't have to worry about R in my formula. So, like, there's two ways to go here. One will be a little less work than the other, not much. But what we need is we need some way to relate our radius on our snapshot to our height in our snapshot. So what we have in here is this is a right triangle, but there is also a secondary similar right triangle at the water height. So in my big triangle, I know my overall radius was 4 feet and my overall height was 14 feet. And then I have my little radius and my little height. So that is the secondary formula that I need here. So I've got big radius over big height equals little radius over little height. My big radius is 4 feet. That's the size of our tank. Our big height is 14 feet. Those two are constant. They do not change. But our little r and our little h, those are going to change based on how much water has leaked out of the tank. So if I take this formula here and I multiply by h, I have my r is the same as, so 4 over 14 is the same as 2/7. So r is the same as 2/7 h. Now, I also could have solved for H here and gotten it in terms of R. But the reason I got R by itself is when I go to substitute into my volume formula, I want it to be all in terms of H. So I only get dH dt in my derivative. So that's why I got R in terms of H. And we're going to make this substitution now before the derivative. But I could also take the derivative of this and get a formula for dr dt. And it turns out dr dt would actually be constant. But so our volume is 1/3 pi. R is 2/7 h squared times h. So we're going to clean this up. So 2 squared is 4 times 1 is 4. 7 squared is 49 times 3 is 147. So I have 4 pi 140 over 147. That's all my numbery parts. Then h squared times h will be h cubed. So there's my volume formula that I'm going to take the derivative of. So dv dt equals 4 pi over 147 times 3h squared times dH dt. Now I know my snapshot height is 12 feet. And I know my volume was changing at a rate of 8 feet per minute cubed. So I'm going to fill both of those in. So this will be a 12. And this will be 8. All right, so 4 times 3 times 12 squared divided by 147. So that gives me 576 pi over 147 times dH dt. And that is equal to 8. Now we should consider here, like the water is flowing out of the tank, right? So our volume is actually decreasing. So this 8 that we plugged in should be negative. Because our height is also going to be decreasing because the water is going out, so the water is lowering. So we should be getting a negative number in the calculation here. So now negative 8 divided by, open, 576, where's pi? Pi divided by 147. So I put that in parentheses when I divided. So dH dt is negative 0.64988. And h is a distance, so that's feet per minute for our time. So we can also deal with volumes, and we end up using our volume formula, but within the volume figure, there's often planar figures that have some similarities that we can make use of within our formula. So a lot of these related rates are just having to remember these formulas and then playing around with what we know about the figure. But like if it's been a while since you've done this, that initial setup can get frustrating. So absolutely, like, visit the math gym, hit me up on GroupMe, like work with a friend. Like having other people to bounce ideas off of can help get this initial setup to work out a lot better. And then you've got all the practice with the calculus, doing the derivative, and then the algebra for solving. All right, so I'll record a video with the last lighthouse question and post that tonight. But I'll get the video of the rest of this posted later today.